Okay, now we are going to discuss about one of the important chapter in boundary layer. So I would like to introduce to you von Karman equation. So if you see our tutorial just now, so it's just a calculation of delta star over delta and theta over delta. So it's, as I said, delta star and theta, it is just an imaginary layer. So it cannot be proved in experimental. We need to calculate the boundary layer thickness, the delta. But until now, there are no equation. You still didn't have any equation to calculate or to find what is the thickness of boundary layer. So, and then if you still remember in my previous introduction, I said that one of the biggest purpose of boundary layer is the calculation of lift force and drag force. Okay, so now we are going to calculate the lift force and drag force. But if you still remember, I said one of the unknown parameter is tau, shear stress. Because previously I explained that we could get pressure by measuring using pitot tube. We could measure the length of the area. We could measure the inclination angle. But it is still difficult for us to calculate or to measure the value of tau, the value of shear stress. Now, by using von Karman equation, we have idea, we could estimate the value of shear stress. Okay, that's why I hope you could give serious attention on how von Karman equation being derived and also how to use von Karman to get the value of shear stress, and finally we could calculate the lift and the drag force. Okay, so in this note, so I will give you the idea of a von Karman equation. Okay, so this is the von Karman equation. So it's introduced by one scientist named von Karman, so from 1881 to 1963. So he used the idea of conservation of momentum. So the idea is very simple. So the sketch is like this. For example, the free stream velocity here. So if you shade the area here, and then after the flow on the flat surface, so it will create velocity distribution, and this is the area of velocity distribution. So previously we talked about the conservation of mass because there are resistance here. So we have no slip condition, so there are resistance there. So the velocity distribution, normally we could assume it will develop like this one. So means that the momentum before and after here is not the same. Okay, and then in introduction, so we need to add another layer here to make sure that it has balance in terms of momentum. Okay, but now von Karman give us another tricks, another idea in terms of balancing the momentum. So what von Karman says that, so the lossless momentum here is actually same with the area in this part. So this is the area, the loss momentum. Okay. Okay, so means that, okay, first we need to know how to calculate the momentum. So momentum is mass time volume. Okay. Okay, I'm sorry. Momentum is mass time velocity. So, and then how to calculate the mass? So we know that rho is equal to mass over volume. So we could calculate mass by multiply rho and volume. So this is the second terms here. Okay, so please be careful. The V here is actually the velocity. Okay, so this is the idea of von Karman. So von Karman says that this area is actually the loss momentum. So we need to calculate what is the amount of the loss momentum. Because the shape here is not linear, mean it is not a rectangular, triangular area like this one. So we need to calculate the area of this one by using the integral method. So first, what we need to do is we assume that we have a very thin layer here. So a rectangular thin layer. So the thickness of this thin area is determined as dy, mean a small portion in y direction, in y axis. So and then the length here, okay, the length here, so from here to here can be written as capital U minus U. So how we could get the idea of capital U minus U? Because we know that this molecule will travel with U velocity here. And then this is the maximum velocity, means the uniform flow velocity. It is capital U. So means from the simple mathematics, we could say that the area here is actually equal to capital U minus U. So here, please make sure that you could differentiate your capital U with small u. So I propose again to write your capital here, capital U here by having U, and you have a bar on it like this. Okay, this is just to differentiate your handwriting between capital and small u, because you need to answer test 1 and final exam by using your handwriting. So please make sure you could differentiate it. Okay, so and then, so the momentum, okay, the mass for the shaded area, the mass for this area, okay, can be written as rho times volume. Okay, this is volume. So this is rho. And how to calculate volume for the shaded area, for the rectangular area here? So we calculate as, okay, so I enlarge the area. So this is the shaded area. So we know that the length here is capital U minus U. So, and then we know that the thickness here is dy. And then we know that its width is equal to B. Remember, we are calculating volume. Okay, so that's why we write here the U minus U times B and times dy. So this is the value of mass only for the shaded area. So and then we could calculate the losses momentum for the shaded area. Okay, so and then the equation for momentum can be written as m times v, means mass times velocity. So this is the mass and the u here is the velocity. Okay, please bear in mind that we need to take the velocity of the molecule. So the velocity of this molecule is actually small u. That's why we write small u here. Okay, please do not take u minus u, because that is not the velocity of that molecule. So and then we need to calculate the total deficit momentum, mean the total loss of momentum. So as you know, because the shape here is not symmetrical, okay, so we need to use the idea of integral calculation. So we integral the idea, so we could simplify as this one. So this is actually the idea from here. Okay, so we integrate this one. So we integrate this one. So we know that the rho here is actually constant. The b here is also constant. So we bring rho and b outside the integral terms. So we could write as rho b integral of 0 to delta u in bracket u minus u dy. So and then what we need to do, we need to apply some tricks. For example, we multiply with u square here, and at the same time we need to divide all of this term with u square. That's why if you see here, If you see here, so we have u over u, and then we have u over u and u over u here. So uh, the total terms here will become u square. So it can be cancelled with this u square. So means the equation is remain unchanged. So please be careful about this. So and then we simplify it. U over u here can be simplified as 1. So and then we have this one. And finally, if we could see this term. Okay, previously in our introduction, we write that theta is equal integral of u over u 1 minus u over u dy. So means now that all of this term can be replaced by this term of theta. So and then to simplify this again to make sure it can be used later on easily. So we differentiate it into dx. So we have d dx equal to rho b u square d theta dx. So we call this as equation number 2. So and then why deficit of momentum occur? So why when we have a plate here, a plane here, so and then the velocity profile will change into this one. So it's occur because there are friction here. So this friction is actually created by or caused by shear stress. As I said previously, as we discussed previously, the viscosity become main victims here. So it gives shear stress, and shear stress will hold molecule tightly and stick on this surface. So what is the equation that could portray, that could illustrate the idea of shear stress here? So as we know previously, we have force is equal tau A. So and then if we have a very small portion, we could say that dF is equal tau dA. So and then this tau, this force actually is actually it is equal to deficit of momentum. So now we write as this one. We write as dd, mean a small portion of deficit momentum is equal to shear stress times dA. So and then, so if we elaborate the idea of A, mean A here is the area. So we know that if we have a plate here, so let's say we are evaluating a very small area here. So if this is the 3D illustration, so the area is this one. So means that the area here is equal to, this is the length dx, and this is the width, which is b. That's why we could replace the dA here with b dx. So and then we bring the words dx here to the left hand side, and finally we could write d dB, dd over dx equal to tau b. Okay, and we call this as equation number 3. And then I think you already know, you could guess, because previously we get dd over dx here, and then the second calculation we also formulate dd over dx. So the next step is we equalize both equations. So we equalize dd dx, which is equal to rho bu square dx, and now it is also equal to tau b. So and then if we simplify this one, means that we could cancel the value of b here. So finally we could say the shear stress, now you have equation for shear stress. So the shear stress is equal rho u square d theta dx. Now this equation is known as von Karman equation. So please remember this equation, and the best, I hope you could derive your own von Karman equation. Means that you need to study from here. So you know how to calculate the momentum. You need to integrate the total momentum loss, and then you could differentiate it to dx. You could calculate another terms of loss deficit momentum in terms of shear stress. You equalize both of them, and finally you could come with this final equation. So please remember that von Karman equation is tau equal rho u square d theta dx. So because this equation will be used again and again in boundary layer as problems. So this is the one that we learned here. So, and then this is just a refreshment. So previously in fluid mechanics 1, we learned about Newton's law of viscosity. So I think you already know about this equation. So I hope you could remember it. Tau is equal mu du dy at y equal to 0. Okay, mu here is the dynamic viscosity. And the du dy here is actually the velocity profile, and y equal to 0, it is the condition. So the condition here, why we always take y equal to 0, because if we have a plane here, and then we have velocity profile like this, okay, we found that the greatest shear stress is actually occur at this location. So this location is y equal to 0. That's why we take y equal to 0 as the condition for the shear stress, because it is the maximum shear stress in almost all conditions.